The next talk of this seminar is going to be given by Yusuke Koide from Nagoya. He was already introduced by Manuel. He's going to talk about something a little bit more fundamental, in particular Lagrangian statistics of turbulence.
Thank you for the introduction. And thank you for coming here, and thank you for giving me this wonderful opportunity to share our recent work. I'm Yusuke Koide, a postdoc from Nagoya University. And today I will talk about the Lagrangian statistics of turbulent flows. And I will consider, and our question is very simple. How universal are the Lagrangian statistics of turbulent flows? And I will consider this question in terms of the hierarchy of multi-scale vortices in turbulence. And this is a collaboration with Professor Susumu Goto at Osaka University in Japan. And before starting the presentation, I would like to mention that we bring Japanese souvenir from us and our friend who stayed here for 2 months. So if you like it, please feel free to try it. And today, in this talk, I will focus on Newtonian turbulent flows in a periodic cube like this. And our focus in this study is on the velocity of fluid particles, which is called the Lagrangian velocity. And first, let me introduce what the Lagrangian viewpoint is, and the reason why I focus on the Lagrangian viewpoint. First, I briefly introduce the Lagrangian viewpoint by contrasting it with the Eulerian viewpoint. In fluid mechanics, we typically use 2 viewpoints to describe flows, Eulerian and the Lagrangian viewpoints. From the Eulerian viewpoint, the fluid flow is described as a function of time and position. So for fixed time, this function tells us the velocity field. So it's appropriate for studying spatial structures of turbulence. In contrast, in the Lagrangian statistics, we don't observe flow at fixed locations. Instead, we track individual particles. So let's consider a particle located at the position x0 at traveling time t0. As the time passes, of course, this particle moves. So then the Lagrangian velocity is defined as the velocity of this particle at time t. So by labeling each fluid particle at its initial position, we can obtain the Lagrangian description of the flow. Since the Lagrangian viewpoint follows each particle, it's suitable for studying transport and mixing properties of turbulence. So then let me explain the reason why I focus on the Lagrangian viewpoint. My original motivation is understanding turbulence modulation by additives, such as polymers and surfactants. I'll introduce this phenomenon using 2 simulation videos. The left video shows turbulent flows of Newtonian fluid. You can observe vortices with different length scales. Remarkably, with the addition of polymers, these small-scale vortices almost vanish. So I briefly explain what is happening here. Polymers are initially in a coiled state in weak flows. Then in turbulent flows, they are advected, and when they meet strong vortices, they are stretched like this. Then these interactions leads to the suppression of small-scale vortices like this. So in this way, polymer dynamics are dominated by the Lagrangian history of turbulent flows, which means Lagrangian statistics are crucial for understanding turbulence modulation. That is why I became interested in the Lagrangian statistics. So next, let me explain about what we actually want to know about the Lagrangian statistics of turbulent flows. As I said before, polymer dynamics are dominated by the Lagrangian history of flows. And our question here is how universal turbulence is in the Lagrangian sense. So as you know, small-scale statistics of turbulence, such as the energy spectra, are universal in the Eulerian sense. But our question is, the dynamics you see when you light with a fluid particle is universal or not? To address this question, we use the Lagrangian velocity, that is a velocity of fluid particles, as a test case. And from this point on, I will focus exclusively on Newtonian fluids and do not consider polymers. Okay, so my first question I come up with is whether the Kolmogorov similarity hypothesis holds or not in the Lagrangian sense. From For Lagrangian statistics, as you know, the Kolmogorov similarity hypothesis predicts that the energy spectrum follows a power law with exponent minus 5/3. And indeed, this scaling law holds for different types of turbulent flows driven by different methods. When it comes to Lagrangian statistics, by applying Fourier transformation to the time series of the Lagrangian velocity, we obtain the power spectral density of the Lagrangian velocity, which is one of the important Lagrangian statistics. And as with the energy spectrum, Kolmogorov similarity hypothesis predicts that the power spectral density follows a power law with exponent minus 2. So I was wondering whether this prediction is correct or not. And this question was solved by previous studies. For example, this previous study experimentally tracked each fluid particle and measured the power spectral density like this. The vertical axis showed the power spectral density of the Lagrangian velocity, and the horizontal axis showed the frequency. The insets showed a compensated spectrum, and you can find the frequency range where the compensated spectrum exhibits plateau, indicating the power law with exponent minus 2. Also, the scaling law is investigated by DNS. Again, this figure shows the compensated spectrum. So this plateau region indicates that power spectral density of the Lagrangian velocity follows a Kolmogorov scaling. So in this way, Lagrangian inertial range exists in the power spectral density of the Lagrangian velocity. However, this does not mean that Lagrangian statistics are fully understood. For example, this previous study measured the power spectral density using experiments and DNS. And this study observed that the power spectral density follows a power law with exponent minus 2 in the high frequency range. However, they also reported minus 5/3 power law in the low frequency range, analogous to the Kolmogorov scaling of the energy spectrum. And according to this previous study, this power law implies the importance of large-scale flows. And similar effects of large-scale flows have been reported in previous studies, in several studies, which means that Lagrangian statistics are not as straightforward as often assumed. Considering these backgrounds, our focus in this study is on the multi-scale nature of turbulence. When you look at the ice surface of the entropy, you only find the smallest scale vortices, which appear to be random. However, using a scale decomposition, you can see a beautiful hierarchy of coherent vortices with different length scales. And fluid particles in turbulence are surrounded by these multi-scale vortices and advected by them. So our question is, how do these different scale vortices contribute to the formation of the Lagrangian spectra? So let me summarize the overview of this talk. Our main question is how universal the power spectral density of the Lagrangian velocity is. To answer this question, we conduct direct numerical simulations by systematically changing Reynolds numbers and forcing methods. To give the conclusion first, universality is observed within a high frequency range, but pronounced non-universality appears due to the largest scale flows driven by the external force. The key point of our study is scale decomposition analysis of turbulent flows, which connects the Lagrangian statistics and these multi-scale vortices in turbulence. Okay, so let's move on to our numerical method. In this talk, we consider incompressible Newtonian fluids. For simplicity, we adopt periodic boundary conditions in 3 directions. And we solve these Navier-Stokes equations using Fourier spectral method. To investigate the universality of the Lagrangian spectra, we adopt 3 types of forcing methods. First, Taylor-Green type forcing, Taylor-Green type anisotropic forcing, which induces 4 vortices shown in red and generates a mean flow in the xy plane. Second, deterministic forcing, which maintains a constant energy injection rate. Third one is a stochastic forcing, which also keeps the energy injection rate constant. And for each forcing method, we conduct DNS at 2 Reynolds numbers. So in total, we analyze the data from 6 turbulent flows. And then let me explain about how to obtain the Lagrangian statistics. During DNS, we track fluid particles by solving their governing equations like this. The Lagrangian velocity on the right-hand side is equal to the Eulerian velocity at the position of the particle. But since fluid particles do not exist on the grid points, we interpolate the velocity value by using trilinear interpolation. Then we obtain the power spectral density by applying Fourier transformation to the time series of the Lagrangian velocity and ensemble average over 32 qubit particles. However, as I said before, the Taylor-Green type forcing induces anisotropic turbulent flows. So we focus, in the following, we only show the results for the x direction, where the mean flow is present for the Taylor-Green type forcing. Okay, so let's move on to our simulation results. So first, I would like to show our main results, the power spectral density of the Lagrangian velocity. And this is a result for the deterministic forcing at low Reynolds number case. Following the Kolmogorov similarity hypothesis, the power spectral density is normalized by the kinematic viscosity, and the angular frequency is normalized by the Kolmogorov time. And this is a result for the same forcing method, but at higher Reynolds number. And here are the results for the stochastic forcing. And finally, these are the results for the Taylor-Green type forcing. And I overplot the Kolmogorov scaling with exponent -2 on this figure like this. So our first observation is that Kolmogorov scaling is observed in the Lagrangian spectra as expected. And next, when looking at the results for different turbulent flows, we find that Lagrangian spectra are universal within this high frequency range. However, significant pronounced non-universality appears in the low frequency range. So in the rest of my talk, we discuss these two observations in more detail. First, let's start with the scaling law of the power spectral density. In the previous slide, I discussed the power law based on this plot. Here, for clarity, we also plot the spectrum multiplied by the square of the angular frequency. And you can find that the compensated spectrum exhibits a plateau within this narrow region, supporting the existence of the Kolmogorov scaling in the Lagrangian spectra. And also, this black dashed line shows the universal constant of 2.1, which is expected value from the Kolmogorov constant. So in this way, a Kolmogorov scaling is observed in the Lagrangian spectra, but within a limited range, like this. So next, we discuss the narrow universality in the Lagrangian spectra. To do so, in this slide, I will compare Lagrangian and Eulerian spectra. On the left are the Lagrangian spectra, and on the right are the energy spectra. And when you look at the energy spectra, you will find that there is a broad universal range. In contrast, Lagrangian spectra exhibit significant non-universality depending on the forcing method. So our question is, what causes this significant non-universality in the Lagrangian spectra compared with the Eulerian spectra? Okay, so let's move on to the discussion. In this part, what we want to do is to understand the formation mechanism of the Lagrangian spectra in terms of multi-scale vortices in turbulence. So our purpose here is to quantify the contributions from each scale vortices to the Lagrangian spectra. To do so, we conduct scale decomposition analysis by using the bandpass filter. What we do is to apply the bandpass filter to the Eulerian velocity. Then we reconstruct the velocity field by using the Fourier components whose wave numbers are within this passband. Using a scale decomposition, for example, from the forests of small-scale vortices, we can extract the hierarchy of multi-scale vortices in turbulence. So then let me explain how to connect the scale decomposed Eulerian velocity to the Lagrangian velocity. As I explained in the previous slide, the Eulerian velocity on the grid points can be decomposed into the contributions from each wave number like this. And here is a schematic of the trajectory of fluid particles. By definition, the fluid particle, the Lagrangian velocity is equal to the Eulerian velocity evaluated at the position of the particle. And as I said before, the velocity on the right-hand side can be decomposed into each contribution by using the bandpass filter. So here, let's introduce this new quantity as a contribution from the flow at wave number kc to the Lagrangian velocity. Then the Lagrangian velocity is also decomposed into the contributions from each wave number. Physically, this scale decomposition analysis enables us to quantify how much scale vortices around this particle contribute to the Lagrangian velocity. Okay, so before discussing the Lagrangian spectra, I would like to show how the scale decomposed Lagrangian velocity behaves. This is a result for the Taylor-Green type forcing, and this black line shows the raw Lagrangian velocity. And this red line shows the contribution from the largest scale vortices shown in red, and this yellow represents the contribution from medium scale vortices, and this blue line shows the contribution from small scale vortices like this. So you will find that larger scale vortices produce larger contributions, and the contributions from smaller scale vortices fluctuate more rapidly, which is consistent with the classical picture of turbulence. So in this way, we can decompose the Lagrangian velocity into the contributions from each scale vortices like this. And using the scale decomposed Lagrangian velocity, we can represent the power spectral density of the Lagrangian velocity like this. And it is important to note that since the decomposition is not orthogonal, the closed terms still remain on the right-hand side. So we have to check the contribution from each term. So first, this red line shows the Lagrangian spectrum itself. And this black dashed line only shows the first term on the right-hand side, which almost collapses onto the Lagrangian spectrum itself. So we can safely ignore the closed terms. Therefore, here we introduce the contribution. Here we introduce this quantity, which appears in the sum of the first term as a contribution from the flow wave number kc to the Lagrangian spectra. These are the scale decomposed Lagrangian spectra at each wave number. And as you go from the top to the bottom, the wave number increases. That is the smaller scales. So in short, by introducing the scale decomposition for the Lagrangian velocity, we can quantify the contributions from each scale vortices like this. Okay, so here, first, to investigate the origin of the universality of the Lagrangian spectra, we will consider the contributions from vortices in the inertial range. And this is a result. Since this plot is very complicated, so I'll explain how to see this figure step by step. So first, the vertical axis shows the contribution from the flow at wave number kc to the Lagrangian spectra. The horizontal axis shows the angular frequency. And different symbols indicate the contributions from different wave numbers, and different colors show the results for different turbulent flows. And the important point to organize these results for different Reynolds numbers, forcing methods, and wave numbers is a choice of variables for non-dimensionalization. The first variable is energy dissipation rate, which I used before. And the second one is a Lagrangian timescale of the flow at wave number kc, like this. So we expect that all the results collapse onto a single curve by non-dimensionalizing with these variables. And indeed, replotting the data almost collapse into a single function like this. So therefore, we conclude that small-scale vortices in the inertial range contribute to the Lagrangian spectra in a self-similar way. So this is the origin of the universality of the Lagrangian spectra. And next, to identify the contribution, to identify the origin of the non-universality, we overplot the non-dimensionalized contribution from the forcing scale on the previous master curve. For clarity, the contribution from the forcing scale is denoted by closed symbols, and the contributions from inertial ranges are denoted by open symbols. And you will find that the contributions from the forcing scale significantly deviates from the master curve, especially for the Taylor-Green type forcing. And this is a snapshot of the vortices at the corresponding scale for the Taylor-Green type forcing. So consequently, non-universal behavior of these largest scale vortices driven by the external force contaminate the universality formed by inertial range vortices. That is why non-universal behavior significantly appears in the Lagrangian spectra. Let's move on to the conclusion. The purpose of my presentation today is to answer the question how universal the power spectral density of the Lagrangian velocity is. And we conclude that universality holds within the narrow high frequency range, but pronounced non-universality emerges owing to the largest scale flows driven by the external force. That's all I have to say. Thank you for your time and attention.
Okay, thank you for your nice talk. Any questions?
Thank you for the talk. It was, again, extremely clear. I have one question that you can see in this picture. Why are the super high frequencies non-universal?
Sorry.
You have non-universal on the left, you have universal on the right, but at the far right, there is a
Okay.
region that by eye I can tell you that it doesn't collapse. And
Okay,
I wonder
so-
why. Is the resolution of the simulations? Is the interpolation? What do you think it is?
There are several possibilities, and I think, so first, these are the results from the random forcing, stochastic forcing, and I think these fluctuations come from the white noise stochastic effect, because the random force I use is the white noise, which means does not have correlation at a long time, so it's very fluctuate. It significantly fluctuates, and so by extracting the contribution from the largest scale flows, which mean driven by the random forcing, they have some deviations here. So I think the deviation you pointed out is coming from the stochastic nature of my forcing. And another reason is, as you said, I use linear interpolation, so it might be coming from the resolution of interpolation, but
But are you not worried that if they are polluting the dissipative range, maybe they are also affecting the inertial range? Which is, maybe your inertial range is also contaminated by the forcing?
So in the inertial range, there are so around here, inertial scale vortices contribute to these spectra, so they are dominant over the contribution from the stochastic forcing. But when you look at the dissipation range, the amplitude is so small that the effect of stochastic nature becomes dominant in this range. So you see the contamination.
Okay, thank you.
Thank you.
Any more questions? I have a few myself. A very nice talk again. I was wondering, because you insisted a lot at the beginning on the difference between the Eulerian framework and the Lagrangian framework. And then once you got the statistics, you wanted to figure out what was happening. And then you resorted to filtering, which to me is sort of a way of going back to the Eulerian frame. Would it make more sense to filter, for example, in time? Have you considered that possibility?
So that's very important point. So you're pointing out the decomposition about the decomposition method, and so I think this decomposition method is not perfect. So what I want to do is to
I understand that this is the standard. This is what I would think of at first if I wanted to do the same as you. But then it came to me the possibility that you can also filter in time. I don't know whether that can be applied easily or what it actually means, but maybe it could be an interesting possibility to.
Okay. So from a theoretical viewpoint, the decomposition in the time domain is suitable, and this decomposition is not theoretically beneficial because this decomposition is not orthogonal in time. So, but I want to get the physical pictures based on the hierarchy of multiscale vortices. So I think there are now I have some ideas to improve this decomposition, and because the trajectory itself is advected by all the scales. So in that sense, this is not the decomposition because the position itself is still advected by the largest scale sweeping. So we have to think about a lot of possibilities still now.
No, I think, at least for me, the Eulerian framework is more intuitive. Whenever I think of this, maybe it's not so much. But okay, maybe something you might want to consider. Okay, so there are no more questions. Remember about the snacks. These guys brought from Japan. Don't be shy. I know you're going to have lunch, but it might be a good thing for you to have something sweet or not so sweet because it's Japanese. But we're going to thank again Yusuke and Rio for their contributions. And